So Chameleon, this gives us a different idea. It's a hierarchical, but also use ideas of graphs. It also comes from a different perspective in terms of what should be considered good cluster. So an overview of Chameleon, I think we want to see that, I want to give you, okay. So the motivation of Chameleon is using distance measures. Those clustering algorithms could cluster these two things in one cluster. They could actually break up this into multiple clusters, if you think of a k-mean. But Chameleon make this observation. This subset and this subset, if you merge them, the new subset have a very similar distribution in terms of data points to the original two subsets. So these two should be merged into one cluster. On the contrary, these two should not, because the density of those two clusters is much greater before you merge them. When you merge them, you have this clear gap in between. So these two, if you take these two things as one whole, you see a different distribution than either of the original clusters. So Chameleon was designed to solve this issue. The clusters it creates have very similar distribution. A look at relative closeness and relative interconnectivity of the resulting cluster as compared to the original clusters. Okay, so that's the motivation why Chameleon is different from others. So how does Chameleon work? We have a data set. We construct a proximity matrix. And here, I put it here very clearly. The data points, the data value here are similarity measures, not distance measures. So those are similarity measures. And then from this matrix, we can construct a sparse graph. The sparse graph is constructed using this. It's k nearest neighbor sparse graph. We will connect the 2 points if P and Q are connected, if Q is among the top k closest neighbors of P. So it's not a fully connected, it's sparse. Only this point and its k nearest neighbor are connected. K, again, is a parameter that user need to set. And with that, so we have this sparse graph, and then the algorithm goes to the next step. We then partition this graph into smaller, tight clusters, very small but tight clusters. Again, the idea of small and tight clusters. How do we partition the graph? There is another parameter called mini size. Everything that I'm talking now is in the slides, in the following slides. So using this minimum size, we will bisect this graph. So bisect means cutting edges so that we divide this graph into two. After we divide this graph into two, and we see whether there are clusters that's greater than the mini size. If it's greater than mini size, we divide that graph by 2 again. So this gives us a set of very tight and small clusters. Then, using this as basically the real input to our clustering algorithm, we can start to build a hierarchical clustering cluster by merge those things. Merge those tight clusters. Merge, again, is based on the two characteristics, the relative interconnectivity and the relative closeness. And we're going to look at those in detail next. So it allows you to, using those parameters, you can actually group, maybe at the beginning, merge these two, and then merge these three, and then merge these three, and then merge additional ones. That allows you merge at a higher level, merge larger clusters. That give you the hierarchical clustering. So K nearest neighbor graph, original data points. One nearest neighbor will connect the points to its closest neighbor. So, and the two nearest neighbor graph, one cluster is, one data observation is connected to two of its nearest neighbor. Three will have more. It doesn't mean that every node is going to have three edges. It will be connected to its closest three, but it might be the closest. It might be among the closest three of other data points. So it's the edge of one node is probably going to be greater than three, but minimum three. Yeah, I think we have talked about this in our first slide.
Question.
Yes.
Go back to previous slide on the previous one. No, the one next. Let's just check.
This one?
Yeah. Okay. So the fact that some nodes in the right figure, in the right one, the fact that some nodes are not connected to each other, does it matter?
It certainly matters. It should not be. So this should not be a fully connected graph. The idea is just use the K nearest neighbor to connect those.
So the fact that, for example, some of them are connected and some of them are not, what does it mean? Aren't all those nodes one cluster?
We don't know yet. So this is the step that we're constructing this.
Okay.
So the K nearest neighbor graph is this graph.
Yes.
From the proximity matrix to this graph, we want it to be sparse, because otherwise the computational cost is just exponential. And then we don't know whether this connected dot is going to end up in a graph, because we're going to cut them. Cut the weak connections to create tight clusters, then merge those tight clusters again to create clusters. So at this time, we don't actually know. Some of them, for example, this one very tightly close together will end up in a cluster, but others may not.
Okay.
The edges are they directed or undirected always?
It's undirected. It's the edges actually is weighted. The weight on the edge is the similarity between two nodes. The similarity is symmetric, so the distance from A to B is the same as the distance from B to A. Other questions? Okay. I think we have already talked about this. So next, we wanted to actually look at the relative interconnectivity. So the idea of using relative interconnectivity is to make sure after the merge. So now we have those tightly tight but small clusters. Our task is to merge them, to see what existing clusters are suitable to be merged. The idea is, before the merge, we can measure the connectivity of the dots in this graph and this graph separately. We want the merged graph have similar connectivity. Okay, so the relative connectivity formula is this. A use edge cut. edge cut between two clusters. So this is merged. So this is C1, C sub I, C sub J. And the merged one is C sub I and C sub J. So this would be after the merge. The edge cut of a graph is the sum of the edge that connects these two clusters. So remember we said the edge has similarity. So you can think of this on the edge, there is a similarity score. The sum of those similarity scores would be the numerator in this case. So using k nearest neighbor, we can actually merge this two graph. And those are the edges that we have. If we cut those edges, sum up the weights on those edges, we get this term. And for this, the lower one, denominators, we look at every graph. We look at the edge cut if we're going to bisect this graph. So divide this graph into two, relatively evenly two clusters. So this is the RI, relative interconnectivity. We want this value to be larger, the better. It's saying that this newly merged thing is equally connected as the original one. So this compare this to this is going to be a good candidate to merge, because if you see if we cut this, it's going to be similar to either of those. And this would be a not that good candidate for merge. So originally we have these two balls. If we merge those two, you can see the cut through here and the cut through here are going to be quite different. Therefore, this is not a good candidate compared to this for merging. The second attributes, the algorithm consider both attributes. So we look at relative interconnectivity, and now we look at relative closeness. So the idea is very similar. It's the merge thing divided by the previous thing. This is weight. You can see MI represents number of data points in clusters C sub I. M sub J represents number of data points in the cluster C sub J. So you can see this is a weighted sum. And this relative closeness using the average, not the sum. The average weight of the edge cut going to tell us how tightly the two clusters are going to be close, going to be connected. So using this previous example that we've seen before, this one going to be a better merge candidate, because you can see the closeness of the original data points and the closeness of the merged graph are relatively similar than this. The merged, the original closeness are very close. Those data points are one next to another. But after you merge, you have this gap, and the distance are larger. Okay, so when we have these two, the original paper proposed two methods that can be used to create hierarchical agglomerative clustering. One is have user specify RI and RC threshold. Then for each cluster, find one most adjacent cluster that exceeds both threshold, and then merge that pair. And merge all the pairs. So at one time, we merge multiple pairs. Repeat the process. But the paper did not implement this method. The paper implemented the second method because it's hard for user to specify RI and RC. So the second method is to using this formula. So we use RI times R2 RC to the power of alpha. And alpha is a parameter that the user need to specify. As you can tell here, we ask user specify 2 parameters, and user have no idea how to specify those. And here we only ask user to specify 1 and alpha. Then user use alpha to control their preferences over RI or RC. So it will be much easier for the user to supply this. The result looks very promising. So Chameleon can actually identify good clusters. And it also, I think, it compared to DBScan, which we're going to talk about later. It achieved a fairly superior result than DBScan. Questions? Oh yeah, the major drawback is it's only efficient for low dimensional data space. In higher dimensional space, the worst case complexity is n squared. That's too slow. It could also happen that the initial sparsification was referring to the KNN step, the creating the nearest neighbor. If the initial smaller tight graphs was not constructed well, then this arrow going to be propagated throughout this hierarchical classification process. So that's a concern. When you have high dimensional data, not only the worst case complexity, the computational time is very slow, but also finding good tight clusters can be challenging for Chameleon. Questions?
And what was A again?
Well, N is a number of data points.
No, A, in the hyperparameters, you have K, min size, and
Oh,
A.
alpha, I'm sorry. Alpha. So here. The alpha is the parameter the user supplies to favor RI versus RC. If alpha is
Okay.
equals 1, then RI and RC are treated equally.
Okay, thank you.
Sure.